second.
While you're putting up the
Slideshow.
slides, perfect. We see the right view. Thank you so much for joining for the second talk of today's dots, the second dot. Deepak Ajwani is an assistant professor at the School of Computer Science in University College Dublin. His research interests include algorithm engineering, combinatorial optimization, and machine learning. He's funded with the Science Foundation Ireland Center for Research Training in ML. His postdoctoral research was supported by the Irish Research Council for Science, Engineering, and Technology and IBM Research. He has more than 50 peer-reviewed top-tier conference and journal publications. He is on the editorial board of Machine Learning Journal and regularly serves as a senior program committee of top AI conferences in the areas of machine learning, algorithm engineering, and optimization. We are very happy to have him here, and please take it away.
Thank you, Alexander, for the introduction, and thanks a lot for organizing this very nice series of seminars, and it's great to be here. Now, the title of the talk is Learning-to-Prune, a lightweight supervised learning technique for solving combinatorial optimization problem, and this is a joint work with my collaborators, Paula, Saurav, James, Juho, another Saurav, Dana, and Jivay. Now, here's a brief outline of my talk today, and I am going to start with the motivation. One of the main motivations for using machine learning for combinatorial optimization problems is that in many applications, the same problem needs to be solved repeatedly on instances from the same distribution. So, for example, in logistics, people often need to solve the vehicle routing problems that come from the same distribution. So it's the same road network, but different customers every day. So we need to solve the same problem day in and day out. Now, a natural question to ask in this context is, can we learn from historical solutions to solve these problems faster? Because the traditional optimization solvers don't really leverage anything from the historical solutions. And what we really like to do is to design efficient heuristics that can learn the characteristics of a particular input distribution and use that to solve the problems faster. Now, this is not the only motivation for using machine learning. Even if we have only one large complex instance to solve, learning techniques can still be useful. And what we can do here is to train on a few small instances and then use the learned model to effectively solve the larger or more complex or problem instance. Okay. Now, over the last decade, a lot of end-to-end deep learning techniques have been developed for solving combinatorial optimization problems. And in this illustration, I'm showing how such a problem can be used for solving a maximum click enumeration problem. So in the maximum click enumeration problem, we are given a graph, and we want to find all the maximum clicks in that graph. So what will happen in this kind of end-to-end deep learning techniques is that they will try to learn everything from scratch. They will ignore all the things that we know about this problem from the algorithmic literature or the optimization literature. I mean, I'm talking about the typical end-to-end deep learning technique. And they will take some representation of the entire graph as an input, and the output would be some representation from which you can extract all the maximum clicks in the graph. Okay. Now, the problems with this kind of approach is, first of all, most of these techniques need a large amount of label training data. And for these NP hard problem instances, this means that you need to solve a large number of problems to optimality to be able to generate that kind of label training data. The other issue is that learning the exact solution often requires deep and complex architectures. The learned model is kind of implicit in the parameters of the model. Okay, so the heuristic that we have learned is not easy to interpret. And what I mean by that is that we do not exactly understand which features were used by the heuristic. we do not exactly understand if I have another constraint added into my problem, will this heuristic still work for that problem, and so on and so forth. Another big issue is that these models, these end-to-end learning techniques learn everything from scratch, and there is no easy way to integrate the insights from the optimization and algorithm engineering literature into these models. And here I should emphasize that real-world applications often involve less explored variants of well-studied problems. So, for example, we have a lot of understanding of the traveling salesperson problem and many of the vehicle routing problems. But now, if in our application we have a new variant of a vehicle routing problem, we don't want to just throw away all the things we know about the solving vehicle routing problems, because over the years we have developed a lot of algorithmic insight, what kind of features work for solving these problems. And rather than learning everything from scratch every time, we should be able to find a way to use all that knowledge. And because of all these reasons, many of these end-to-end deep learning techniques struggle to generalize to larger problem sizes and out of distribution inputs. Although the results are improving in this regard, but still this continues to be one of the pain points. So this is where the Learning-to-Prune framework comes in. For the sake of simplicity, I'm going to focus here on binary integer problems. The framework itself is quite general, and I can talk about, and in the question answer session, if somebody is interested, I can talk about how the framework can be generalized to more optimization problems. But for here, let's focus on the binary integer problems where the variables can be either 0 or 1. Okay. So we are going to view this as a classification problem to discriminate between variables that have the value 0 in the optimal solution from the variables that have the value 1. So for example, here I have a figure of for a vertex cover problem. So here the variable value 1 corresponds to vertices that are in the optimal vertex cover. The variable value 0 corresponds to vertices that are not in the optimal vertex cover. And the goal of the classification task is to separate the vertices that will be in the optimal vertex cover from the vertices that will not be in the optimal vertex cover. On the right side, I have a traveling salesperson problem instance. So here we want to discriminate between edges that are in the optimal TSP tour from all the remaining edges. Okay. So the point is that we can view the binary integer problems as a classification problem. Now, if we want to fix all the variables in the binary integer problem, that is what the end-to-end learning techniques do. So in this picture here, I am representing the variables that have the value 0 in the optimal solution with the brown ovals, the variables that have the value 1 in the optimal solution with the yellow stars. And our end-to-end learning techniques try to learn a decision boundary that clearly separates all the variables that get the value 1 in the optimal solution from all the variables that get the value 0 in the optimal solution. And this, as we know, is a hard challenge. Instead, what the Learning-to-Prune framework tries to do is to learn a simpler, relatively simpler decision boundary such that all the variables on one side of that decision boundary belong to one class. Okay. So maybe all the variables on one side of the decision boundary have the value 0. So now we can fix all those variables. So that's the high level idea of Learning-to-Prune. Just to illustrate it a bit more clearly, this is a facility location problem instance. So the red points here correspond to facilities, and the blue things here correspond to the clients. This is now my optimal solution for this problem. And what the Learning-to-Prune framework will try to do is to remove some of the facilities that are not in the optimal solution. Okay? So it may not be able to remove all of the facilities that are not in the optimal solution. So you can see here that some facilities that are not in the optimal solution are still there, but it will try to remove as many as it can confidently predict. Now, once the problem size is reduced by fixing some of the variables, we can then solve the remaining problem using an existing algorithm or heuristic. And in this case, if the pruning didn't delete any element of the optimal solution, the optimal solution is preserved. We are very happy. But sometimes we mispredict and elements from the optimal solutions are lost. Nonetheless, in most cases, we do get optimal or near optimal solution in a fraction of running time of the exact algorithm. And that's where the power of this framework lies. Now, I should say a little bit about the different type of pruning that we can do. So one is the hard pruning, where we remove the pruned elements from the problem altogether. The other is the soft pruning, where instead of removing elements, the pruned elements altogether, we actually add a constraint that states that at most a small fraction of the elements in the optimal solution can be from the pruned set. So we have introduced a new constraint to our problem, and this constraint often reduces the search space drastically and greatly speeds up the computation. Now, just as in the case of Vissen, what she talked about, an important part of this learning framework is the features that we get. Now, you can, of course, get the features from the graph representations, and they can be very generic. But we can also have problem-specific features in this case, and they can come up from the algorithm design, algorithm engineering, and the optimization literature. And the intuition here is that it is often easy to find some signals that are possibly correlated with the optimal solution, and these can come from related problems that have been well studied theoretically. So the features can be derived from quantities that are used in the approximation algorithms or heuristics. The features can also be derived from operation research literatures. For example, the linear programming relaxation is often a very, very useful feature. We can also have some statistical features and some features that capture domain knowledge of the problem. Now, what about classification model? In our experiments, we found that the classification model didn't really matter so much, in the sense that the different classification techniques that we tried, all of them gave us roughly the same kind of results. But one thing I should say is, just as in the case of Bayesian stock, we also use random forest, and for the same reason that it provides easy to interpret feature importance. So our goal was to design new heuristics, because I come from an algorithm engineering background, and we wanted to design new heuristics. And having this feature importance is actually very useful in understanding what has the algorithm learned, and we can use that to come up with new heuristics. I will give an example towards the end of this talk. Now, we don't need to stop at a single stage of pruning. We can prune repeatedly to learn increasingly discriminative classification models. Now, there are some engineering details that we need to be a little bit more careful about. For example, if we prune too much, we can prune out all the feasible solution, and we may end up with something that is infeasible, even though my original problem had a feasible optimal solution. So one way to deal with this issue is we can have solutions returned from some known algorithm, and we can ensure that those solutions are never pruned. But in practice, we found that just repeating the pruning process with less aggressive thresholds is often enough. Now, what are some of the big advantages of this Learning-to-Prune framework? So this is an extremely simple framework, and that can be used in a whole lot of different optimization problems. We don't need to restrict ourselves to one particular solver or one particular type of features. We can use it in many different contexts. So one big advantage is that Learning-to-Prune is parsimonious with the training data, and it usually requires only a few training instances. So typically we use only 5 to 20 training instances. So most of the results that I'm going to show you next are based on very, very small amount of label training instances. Then next is that because it uses simple localized features and existing algorithm, we are able to capture the domain knowledge. We are able to capture algorithmic insight into the learning framework. And here again, I should mention that if we have a well-studied variant of the problem, we can use the features that are derived from that well-studied variant. And Learning-to-Prune can be done using more interpretable classification models with fewer parameters, and therefore we can understand exactly which features have been used to what degree in the learning framework, in the learned heuristic. Models generalize better to larger size instance, and this is something that I'm going to show you very soon. And they also result in the design of newer and simpler heuristics. So let me move on to the results. So the first thing that I want to show you is the problem of maximum clique enumeration that I pointed out earlier. So this is a problem where we want to find all the maximum cliques in a graph. And what we see here is that with some very simple statistical features, this Learning-to-Prune framework is able to prune over 99% of the nodes in these sparse social network graphs that are part of the benchmark suite for this problem. And this then results in a significant speed up. So for example, on one particular graph, we got down from 40 minutes down to 7 seconds. And then what we see here is that despite this significant speed up, we are able to obtain fairly high accuracy. In all of these instances, we found the maximum clique of the correct size. And not only that, we actually found most of the maximum cliques in the graph. Okay, so you see that almost all of the maximum cliques were preserved in the prune graphs, and we could find them very fast. So next, I want to show you the results of the Learning-to-Prune on the Steiner tree problem, and this is from the SteinLib dataset. So here again, we see that we are able to reduce the running time by around 99%. So the running time would come down from many, many hours using Gurobi to something in just a few minutes. And the loss in the objective value is a very small percentage. So we are very close. So we find near optimal solution in very little running time. Now, another interesting thing that we observed from this Steiner tree problem was on the pace challenge data set. Now, on this pace challenge data set, we had two tracks. The track 1 contained instances with a small number of terminals, and the track 2 contained instances with small tree width. So we trained the model on some very few instances from track 1. And we found that this model was actually very effective on the track 2 instances as well. We did not give any hint to our model that these instances had the special property of small tree width. Tree width was not a feature used in the training data, but nonetheless, the model was quite effective on the track 2 instances as well. So what we see is that because we are using so much of the algorithmic knowledge in our learning process, our learning model is actually quite robust to changes in the input distribution. Next, I want to talk a little bit about the k-median problem. Now, on the k-median problem, we compared our results with the Charika-Lee approximation algorithm. Now, this is an approximation algorithm that was specifically designed for metric instances, instances where the distances follow the triangle inequality. And on these instances, we use some features that were also derived from this approximation algorithm. So then we found that this learning to prune approach could provide comparable or better optimality gap on these metric instances. But what was more interesting was the comparison on the non-metric instances. So we took some random k-median problem instances with a certain number of facilities and clients. And what we saw was on some fairly difficult random instances, non-metric instances, where the approximation algorithm of the Charika-Lee fails completely, there is a huge optimality gap for this approximation algorithm because this is a non-metric instance. This algorithm was not designed for non-metric instance. Even the bespoke genetic algorithm was performing extremely poorly on this instance. We see that these hard pruning and the soft pruning approaches give us near optimal solutions. So the important lesson for us was that even though the features we used in the learning to prune were derived from the approximation algorithm that was designed only for metric instances, the use of this feature also led to significant speed up in the non-metric instances where the original approximation algorithm failed completely. So this was a very important lesson that we learned from this particular experiment. Now, one of the criticisms that we had from the first time we submitted this paper was that we are comparing our running time with the optimization solvers, and these solvers actually spend a lot of time verifying that the solution that they got is correct. We should actually be comparing ourselves with the good solutions that they produce early on in the search process. So we took that feedback on board, and we compared ourselves with a commercial solver. So in this case, this is FICO Express MP, but the results are very similar with the Gurobi as well. And this is the trade-off between the optimality gap and the running time that we get with the FICO Express MP. So this is with this green curve. So this is the solutions as we get while the solver is working on it. And we see that with our hard pruning and the soft pruning approach, we get a much better trade-off. So these are minimization problems. So that means that the trade-off on the bottom left side is a better trade-off. And we see that our hard pruning and soft pruning approaches actually give us a better trade-off. Now, I mentioned that what we wanted to do was to train on a few small instances and then to be able to solve much larger instances of the problem. So that's our goal. So does the model generalize to larger instances? And in this case, we see that, again, I'm going back to the k-median problem, and I'm going to these harder non-metric instances of the k-median problem. So we trained something on instances with around 100 nodes, and we tested on instances with around 200 nodes. And what we see is that while the commercial Express MP solver found a solution with a value of around 441K after many hours, uh, just by learning on a few instances, I think it was only 5 instances in the training, the hard pruning of the learning to prune model found a solution of a much better value in just 45 seconds. So this kind of shows you that we can actually use it to solve larger instances of the problem, and the model actually generalizes very well to larger instances. Then we looked at if we can generalize to even larger instances, and that's where we thought of how we can do the bootstrapping of the learning-to-prune model. And the idea here is that we can improve the results of this model by running a local search to improve the solution, or by using it as a warm start in the MILP solver, mixed integer linear programming solver, and running the solver for a limited time. So these are standard techniques to improve a solution. So what we can do is we can start with small instances that we can solve using a mixed integer linear programming solver. We pass the optimal solution and learn a classification model from those optimal labels. Then we look at the intermediate size instances. We use the classification model to prune those instances. Okay. Then we can solve those pruned instances using a mixed integer linear programming solver and use this local search or a warm start to improve those solutions. And then we can improve the classification model based on those improved solutions that we have found. And the updated classification model is then used to solve the large instances. So we then use the updated classification model to prune the large instances and then solve those using the mixed integer linear programming solver. So this then gives us good solutions for our large instances. So does this bootstrapping technique actually work? So again, going back to the hard non-metric instances of the k-median problem, this time we look at instances with 1,000 clients and 1,000 facilities, and we see that even this bootstrapping actually provides us significantly better results compared to just training directly on the small instances and testing on large instances. Okay, so the bootstrapping allows us to get a much better objective function value. Of course, this comes at the cost of increase in the running time. We may spend a factor of 2 more in terms of the running time, but we have to note that once it gets closer and closer to the optimal value, it actually becomes harder and harder from a time point of view to improve the solution. So actually, these results are quite good in that sense. So I just want to bring some discussion points here. So one is that one of the big side advantage of this is that we can use it to learn new heuristics, and that was one of my main motivations to look into this framework. So typically, most of the feature importance is captured by very few features. So we can actually use a combination of the most discriminative features to design new heuristics. So for the maximum clique problem, my colleagues found that on dense graphs, the average chi-squared neighbor degree was one of the most discriminative feature. And so they designed a heuristic for maximum clique for dense graph that was based on this average chi-squared neighbor degree. And they found that it outperforms all the state-of-the-art heuristics for this problem on dense graphs. So we actually managed to discover a good heuristic with our Learning-to-Prune framework. Now, of course, this is not a one-size-fits-all for all the combinatorial optimization problems. There are some limitations. In particular, this framework ignores the correlation between the variable values in an optimal assignment, and there are issues in how we deal with the symmetry in problems. We also need features for the variables. And in case variables belong to different categories, sometimes this can get tricky. There are also issues in generalizing to non-binary optimization problems. And lastly, I would actually like, I haven't found any theoretical explanation that would prove that actually simple decision boundaries are often enough to prune large parts of the search space. In our experiments, we find that this is often the case, but I would like to see a kind of a theoretical explanation for this phenomenon. So with this, I come to the end of this talk. Thank you all for your attention, and I'm happy to take any questions.
Thank you, Deepak, and thank you everybody for attending both dots today. I think that we are basically at the breakout room time, and that'll be a great place for you to take in questions. So what I'll do is I'll stop the recording here. I do want to briefly say that we do have another session of dots in a month. Off the top of my head, I don't remember. November 11th, maybe I want to say it's a second Friday of the month. So I hope you all can join us for that. But if you do have any questions, please stick around, or if you just want to socialize, that's also one of the ideas behind the Zoom breakout rooms. So thank you again to both speakers today.